The following videos might help you more know about the limits.
All right, let's jump right in. We're going to tackle one of the biggest ideas in all of calculus, the limit. So, take a look at this function. You might think, what's its value when x is exactly 2? Well, if you just plug in 2, you get 0 divided by 0, and that's a big problem. Yep, that's undefined. So, how do we find an answer when there isn't one right at that spot? And this is where the limit comes in. It's all about the value the function approaches. This is just the fancy math way of writing it. It's asking, what value are we getting near? Okay, so how do we actually find a limit? Let's open up our toolkit. First up, direct substitution. A lot of the time, you can literally just plug the number in. It's that simple, it just works. The process is super simple. You just replace x with the number and then calculate the answer. So for this example, we pop a 3 in for x, solve it, and boom, there's our limit. Easy. But wait, let's go back to our first problem. Direct substitution totally failed us there, remember? We got undefined. So what now? Well, this is where we need to pull out some clever algebraic tricks. Time for our next tool, factorization. This is all about simplifying the problem before you solve it. So here it is again, our undefined problem. We know plugging in 2 is a no-go, but what if we rewrite it? Watch this. We can factor the top part, and look, we get an x minus 2 on top and bottom. And since it's on the top and bottom, we can just cancel it out. The whole problem part is gone. Now we just plug 2 into what's left, which is super easy, and our limit is 4. But what if you've got a square root in the mix? For that, we need another trick, the conjugate method. And you guessed it, plugging in the number gives us 0 over 0. That square root is the key. The magic trick here is multiplying by something called the conjugate. You just flip the sign in the middle. This clever multiplication gets rid of the square root, so we can simplify, cancel, and find our answer. So why should you care? Because limits are the absolute foundation of calculus. They unlock everything else. Think of it this way. They let us study change itself, from the infinitely small to the infinitely large. So here's a final thought. What if you applied this idea elsewhere? What problems could you solve by approaching them? Welcome to The Explainer. We're jumping right into a huge idea in calculus, the limit. So let's start with a puzzle. What happens when your math just breaks and looks totally impossible? This is the central idea. A limit isn't its actual value, but what it's heading towards. The great thing is, limits aren't random. They have a logical structure, starting with some basic rules. You can add them. Simple as that. The limit of a sum is the sum of their limits. Yep, you can subtract them too. The limit of a difference is just the difference of the limits. You guessed it, you can multiply them. The limit of a product is the product of the limits. And you can divide them, just as long as that denominator isn't heading to 0. Predictable, right? So how do we find a limit? Well, we start with the simplest method first, direct substitution. And it's as simple as it sounds. You literally just plug the value right into the function. So we take our function, plug in 3, and solve it out. A lot of the time, it's that easy. But what happens when this easy way gives you an undefined answer, like 0 divided by 0? This result, 0 over 0, doesn't mean the limit is gone. It's a signal to find another way. When direct substitution fails, we bring in the algebraic tools to simplify the problem first. Our first tool, factorization. This is perfect for those messy fractions with polynomials. The process is awesome. You factor, cancel out the term that's causing the zeros, and then substitute. All right, but what if you see a square root? That's a job for our second tool, the conjugate method. You multiply the top and bottom by the conjugate, which often clears up that problem term. Magic! So how do you pick? If it's a fraction of polynomials, you factor. If there's a square root, conjugate. So remember, limits aren't about what's at a point, it's about what the function is getting close to. And the core idea here is undefined is never the final answer. It just means find another way. And why does all this matter? Because limits are the foundation for, well, all of calculus. So now that we can get past undefined, what other mathematical mysteries are you ready to solve? Hey everyone, and welcome. Today, we're jumping into one of the most common hurdles you'll face when you're starting out in calculus, finding limits. We're going to talk about what to do when the most obvious path leads you, well, straight to a dead end. I mean, you've been there, right? You're working on a problem, you're following all the rules, you plug in the number, and the answer you get just doesn't make sense. It feels like you've just hit a brick wall. And this is usually the culprit. 0 divided by 0, undefined. For years, we're taught that this is just wrong, a total stop sign. But here's the secret. In calculus, this isn't an error message. It's actually a clue, a little hint telling you to look at the problem in a new way. Okay, so let's break this down. The very first move pretty much everyone learns for finding a limit is called direct substitution. And honestly, it's exactly what it sounds like. You just take the number that x is getting close to and you plug it right into the function. And you know what? A lot of the time, this simple method works beautifully and gets you the right answer in seconds. It should always be the very first thing you try. But we're here to talk about those tricky situations where direct substitution gives you that dreaded, undefined result. So what do you do then? Well, let's pull out our first tool from the toolkit, the factorization fix. This is a really powerful algebra trick that lets us simplify the function, get rid of the part that's causing that whole 0 over 0 issue, and find the answer that was hiding there the whole time. Let's work through this exact problem right here. We're trying to find the limit as x gets closer and closer to 2. So if you plug in 2, on top you get 4 plus 2 minus 6, which is 0. And on the bottom, 2 minus 2, which is also 0. So, dead end. Or is it? Okay, step 1. We gotta factor that numerator. We're hunting for two numbers that multiply to -6, but add up to +1. Let's think. How about +3 and -2? Let's check it. 3 times -2 is -6. Perfect. And 3 plus -2 is 1. That's it. So we can rewrite the top part as x plus 3 times x minus 2. And right here, this is the magic moment. See that? We have an x minus 2 on the top and an x minus 2 on the bottom. Since they're the same, we can just cancel them out. This is the whole key. We just algebraically removed the exact thing that was causing the problem. Now look what we have left. After canceling, our big, complicated problem just becomes finding the limit of x plus 3 as x approaches 2. And this is so much easier. We can go right back to our original method, direct substitution. All we have to do is plug in 2 for x. And boom, there's our answer. 2 plus 3 is 5. That's the limit. It was there all along. It was just disguised by that tricky 0 over 0 form. All right, let's switch gears for a second and look at a totally different kind of limit puzzle. These are called piecewise functions. You can think of them as having a split personality. They follow one rule for some numbers and a completely different rule for others. Take a look at this one. If we approach -2 from the left side, from numbers smaller than -2, we have to use that top rule. Plugging in -2 gives us 2 times 4, which is 8, minus 5, so 3. Now, if we approach from the right side, from numbers bigger than -2, we use the bottom rule. Plugging in -2 gives us 6 plus -2, which is 4. The function is heading towards two different numbers from either side. So that brings up a really interesting question. If we want the limit at exactly -2, which rule are we supposed to follow? The point itself is the border between these two completely different behaviors. So, as we just saw, the trick is you have to check both sides. The limit from the left gave us 3, and the limit from the right gave us 4. We're basically sneaking up on -2 from both directions to see if the two paths meet up at the same spot. And that leads us to the single most important rule for these kinds of functions. The overall limit at a point only exists if the answer from the left is exactly the same as the answer from the right. They have to agree. In our example, we got 3 from the left and 4 from the right. Since 3 does not equal 4, the overall limit at x equals -2, well, it just doesn't exist. Okay, so let's wrap all of this up into a clear strategy. You're not just learning a bunch of random tricks here. You're building a real toolkit for solving any limit that gets thrown your way. Here's your game plan. Number 1, Always try direct substitution first. It's the easiest and fastest way. Number 2, if you get 0 over 0, don't panic. That's your clue to dig a little deeper. Number 3, use factorization to simplify things and cancel out those problem terms. 4, if you see a piecewise function, remember you have to check it from the left and from the right. And finally, number 5, that limit only exists if both of those sides are equal. So there you have it. You've learned how to turn a mathematical dead end into a signpost that points you right to the solution. Undefined isn't a stop sign anymore. It's a challenge. And now that you have the tools to beat it, what other calculus puzzles are you ready to take on?